All right, looks like we're good to go. All right, so just by way of quick introduction, we just got introduced there, but the folks on the stage, I'm Michael, CEO at AssetNote. I have Shubs, CTO at AssetNote, Sean on the end, engineering lead, and Pat, senior engineer. So we'll be presenting today, but there are actually a few other contributors as well. So we've got James down in the audience, and Jordan there, also work with us at AssetNote. Had a bunch of interesting contributions, especially the killer ASCII art. That was James's contribution, so plus a few other things. So we're going to be talking about content discovery today. So when it comes to web application security, and particularly offensive web application security, content discovery is a really key element. So when you think about an organization and their attack surface, the application attack surface is often very large and varied. And understanding as much information about that attack surface is critical if you're looking to find security bugs. So to do this, you typically do some sort of content discovery. And typically that involves file and directory brute forcing across those web assets. And the more effective you are with this, the more you can map out the application attack surface, and the more likely you are to find various avenues for exploitation. Pretty straightforward. So if we look at the current state of content discovery and where it's at. So as I mentioned, the typical approach to content discovery is just file and directory brute forcing using a word list. There are a number of great tools out there that are commonly used. So, there's WFuzz, DirSearch, more recently, things like GoBuster, FFuff, RustBuster, FerrexBuster. And usually these tools are paired with some sort of hand-curated word list, maybe from a source like Seclist, or maybe something that you've built yourself and added to over the years. And so these tools have evolved over time, but ultimately the underlying approach has remained the same. You have the tool, you feed it a word list, and you feed it a list of assets that you're pointing it to, and it goes there. So, and there have been a number of improvements, though, over the years. So things like flexibility of where you can fuzz, better ways to filter out the content and the output. But really, at the end of the day, there hasn't been too much innovation in terms of the content discovery techniques. It's still ultimately doing the same thing. Generally, each iteration and each new tool is really primarily focused in a lot of ways on going faster. So that's why you see sort of the evolution from sort of Python to Go to Rust. It's really designed, they're really optimized for going fast. And this leads to kind of a cycle that reinforces itself. So more speed, you can run a bigger word list against your target. The faster the speed, the more web apps you can cover in a shorter amount of time. And then if you add in sort of recent asset discovery tooling, it kind of completes the cycle and it just reinforces itself. And that's been really most of the innovation in that sort of space in terms of content discovery, more about speed. And given a large enough attack surface, this approach can still be pretty effective. However, application development has also evolved. If you think about modern application development, it's primarily framework-driven. It's typically API-focused with complex routing. And modern applications have generally moved beyond this paradigm of files on a server to being with endpoints that are more strictly defined in code. And so while there has been some movement in the tooling towards more context awareness, so things like CommonSpeak and even our wordless site, which sort of auto-generates these word lists, most of the tooling lacks context. So what do we mean by when we talk about context awareness? Context awareness allows us to discover more API endpoints than typical content discovery tools that simply guess for files and folders without any of the context. And as we mentioned earlier, the more endpoints you discover, the larger the attack surface, and the higher the chance that you're going to find some sort of security vulnerability. Without the context awareness, certain APIs might not even respond at all. And with that, you're probably missing a lot of the attack surface. And so the only real way to really cover that attack surface with modern applications and modern APIs is through context awareness. Ultimately, you can't hack what you don't know is there. So let's dive into this concept of context a little more with some concrete examples. So if you think about frameworks, right, they want really well-defined APIs. So, legacy systems, they're defined by, files on a server ultimately. But as frameworks such as Flask and Rails and Express started to become more commonplace and they took over, it's not really the way that things are structured now. So when modern frameworks became more prevalent, we noticed that endpoints were no longer just files on the web server, but rather they were strictly defined APIs in the code of the application. And so this has fundamentally shifted the way that we see content discovery. As we're no longer just searching for files and folders, we need to specifically look for these API endpoints. So to run through some simple examples, so we'll start with Flask. It's a very basic sort of a bit of code here, but there's a number of different elements of context. So the first one is there's a parameter in the path there, which is this key parameter which takes an integer value. So that's the first bit of context that you need. If your word list doesn't have, /1, 2, 3 or something like that on the end, you're not going to be able to hit this endpoint. If you look at the rest of the code, there's also a number of other elements of context. Specifically, it's responding differently and handling things differently based on the HTTP method that has been supplied to it. So, for example, we've got different output for put, delete, and for the get, if it's not found, if the key's not found, so it's not in your word list, you're going to get an exception that's not found. So let's imagine, say, that get, the sort of the default there for the get is not there, and it's just put and delete. If you've got a word list that's just running through, even if you have like an integer in that parameter value, if you're not configuring your brute forcing to hit or to use a put request or a delete request, you're going to miss this entirely. In a similar vein, we've got an example with Rails. Again, multiple parameters in the path. So in this case, we've got this to-do ID and also an item ID. And again, different combinations of these parameters as well as request types. Doing different things. So again, in this case, it's responding to post, put, and delete with various context in the path as well. And so again, if you're brute forcing with just get requests, you're likely, well, you will miss all of this, right? So unless you're configuring specifically to look for this stuff, you're going to miss this attack surface. And then finally, again, with Express, another simple example, but here we've got three parameters of different types in the path. So again, unless you're brute forcing with that context in there, you're going to miss this endpoint entirely. So even these simple examples demonstrate how contextually understanding an API is important for effectively mapping out the application's attack surface from a black box perspective. Subtle changes in the requests that you send can produce dramatically varying results and can be the difference between discovering a valid endpoint or not. And current approaches to content discovery tooling don't really account for this context. So we decided to work through this idea of context-aware asset discovery. So context-aware content discovery is the process of finding endpoints in applications by sending requests with context. So when we talk about context, I'm talking about things like the HTTP method, parameters, values, headers, things like that. And it aims to tackle the problem of modern APIs that only respond when the correct context is being sent to them. And so, like we went through in the previous examples, some APIs expect certain methods, certain parameters, values, or headers when they're being requested. By making brute force attempts with the correct context, we can discover modern API endpoints. So what did we do? What was our approach? So to solve this problem, we decided to build a tool and a data set that is capable of sending these API requests with the correct context. So API specs such as Swagger define how APIs operate and exactly, to a high degree of specificity, what methods are required, what the parameters are, what types of values should be in those parameters, and any headers that are necessary to interact with those APIs. So we then made it our mission to collect as many Swagger specification files from across the internet, broad internet-wide scanning, and then we built a data set from all of the API specs collected, and then we built a tool that was capable of using this data set to send fully formed contextual requests to web app servers for content discovery.
So the next part was collecting all this data, getting all these Swagger files from the internet. So I'll go through a little bit how we did that and all the different sources we ended up using for this. So first off, we use BigQuery. I've talked about BigQuery quite a lot. It is quite magical. It lets you query terabytes of data in seconds. It's also really amazing because it has GitHub's public dataset. GitHub's public dataset isn't exactly the entirety of GitHub on BigQuery, but it is a decent portion of GitHub. And through that dataset, we were able to query it and obtain all of the Swagger files from it. So this is what our query looked like from BigQuery. We first queried from the files table to find anything that ended with swagger.json, API docs.json, or openapi.json. And then finally, we obtained the contents of these files by running the second query shown on this screen. So after we obtained all these files, we had to parse the CSV file that was outputted. And then we obtained all of the Swagger files individually through this process. We now have 11,000 Swagger files. These are deduplicated and unique Swagger files. So we've already got 11,000 Swagger files through this method. Next, we took a look at apis.guru. Now, this project is pretty interesting. Its goal is to create a machine-readable Wikipedia for REST APIs. It's entirely open source, and it documents publicly accessible APIs with Swagger definitions. All the data from the OpenAPI directory can be accessed through a REST API itself. So we downloaded the REST APIs via a REST API. That's Inception, I know. But we extracted all of the Swagger API endpoints from it, and we were able to use something like wget to download all of these Swagger files. So it just looks something like this. We just downloaded all of these Swagger files from apis.guru. We ended up with 14,000 unique Swagger files cumulatively at this point. Then we also found another data source, which was Swagger Hub, and we could list all the specs on Swagger Hub, and unfortunately, it was only limited to the first 10,000 results. That was a limit that they were enforcing on the server side, not something you could bypass with a list of IPs, with a list of proxies or something. It's just a hard limit of 10,000. But supposedly, they have something like 400,000 Swagger specs in their database. If we could grab that, that would have been amazing, but we were only able to grab the first 10K. We weren't able to bypass these limitations in any obvious way. This was written in async Python. We downloaded around 10K Swagger files through this method. We ended up with roughly 23,000 Swagger files by the end of this. And then lastly, I guess the most important part is we scanned the internet. So James on our team spent some time scanning the internet, and we did some calculations. There's 3.7 billion IPs on the internet that are accessible. And we didn't scan IPv6, but that is what it would look like if we scan IPv6, the number at least. And we scanned port 80 and 443, HTTP and HTTPS. And we scanned 22 different paths where we thought that Swagger files could be available. And as James mentions in these slides, if you want to frustrate hackers, return a crisp 200 on all routes instead of a 404. Why not make all pages have the content type of application JSON? So these are the paths that we scanned and the number of hits that we had. You can see that some routes are much more popular than others. Like, for example, V2 API docs had 27,000 hits, and API V2 swagger.json had 91,000 hits. These statistics are before we have done our deduplication. So these are just the raw statistics from the internet-wide scans. And our approach was something like this. We skipped IPv6 because we're not going to be scanning that many IPv6 addresses, and technology is not there yet to be able to scan that many addresses. We preferred passive sources to supplement our data. So we used the Rapid7 HTTP and HTTPS datasets combined with an internet-wide mass scan to fill in the deltas. As I said earlier, we only stuck to port 80 and 443, as we knew that production servers predominantly use these ports. Future scans, if we want to develop this out further, we could look at other ports like 8080, 8090, 9090, things like that development servers could be running on. But at the moment, we only focused on 80 and 443. We focused on known API documentation paths, and we scoped it to Swagger 2.0 compliant files. So the process and the infrastructure, we only had one 8 GB Linode box, and Linode is a great provider to do internet scans from. They're very friendly to security researchers. So I highly recommend them if you're looking to do something like that. We set up an RDNS record, and that's something that we suggest you do as well, where you just explain the scan traffic. This way, it reduces the number of abuse requests significantly, and you can continue going on with your business without any problems. The software we use MassScan to fill in the deltas. We use zgrab2 to obtain the Swagger files and communicate on the HTTP and HTTPS protocols. And we use some custom validation tooling that we built in-house. It looks something like this. We patched zgrab2 to add an API specification detection module. So every time it would detect a Swagger JSON file or Swagger YML file, it would flag it. But it would be making these 22 requests that I showed earlier across every single host that we had identified being online on port 80 and 443 on the internet. So we fed these IPs to zgrab2, and at the end, we ended up with roughly 20 gigs of output that we had to deserialize and deduplicate. So here are some numbers. So it's quite a lot of hosts that we scanned at the end, quite a lot of valid data returned, but the post-processed unique routes were sitting at just under 1 million. So quite a lot of routes that actually gave us data. So we ended up with, after deduplicating, we ended up with roughly 67.5K Swagger files. So that's a pretty decent data set, and we will be releasing that later today as a part of this project.
So next, we had to parse all this data. Why? Because we have a ton of Swagger files, and we want to basically meet a number of conditions. We don't want to include any invalid specs. We want to exclude all our duplicates. A lot of these specs were like the Swagger pet store example, so obviously useless to us. Anything that's blacklisted, so we can include in our parsing tool a list of blacklisted hosts that maybe they offer a bunch of generic specs that aren't very useful to us. So we want to be able to offer a way to exclude these from being included. We want to add any missing parameters or replace any invalid parameters. So in some of these specs that we have, they'll have path parameters in the path, but not defined in the actual parameters inside the spec for whatever reason. So we want to be able to detect these and include them so that we can use them later on in our other tooling. We want to try to detect any UUID or regex parameters and mark them as such so we can accurately guess those parameters when testing the APIs. And we want to add a KSUID to each spec so that when we're running our tooling, we can trace back to the original spec where this problem was coming from. And we want to be able to pass this into a single file so that we can use Kiterunner to compile the word list. So we want to conceptualize the data. We had some basic rules, like the ones I mentioned a moment ago, as well as we wanted to replace any JSON ref values because it becomes very difficult to try and do this at a large scale unless you just do it each time you process an individual spec. We want to include the security definitions, excluding the LWRF2 because they're kind of irrelevant, as well as the host or the URL that the spec came from. And if a string appears to be either a UUID or a regex, we want to mark that format as such. And do our best to deduplicate any results that have come through. This is an example of what I mean by a path that doesn't quite include the token in this case. So we want to add that to the path so our tooling is able to fill those values and guess what it can. And so what does this output look like? It basically looks like a bunch of these, where you've got the KSUID, URL if it's included, any security definitions if they're included, as well as a bunch of paths and parameters. So writing the tool, we want to write it in Python because it's easy to work with JSON data and manipulate the data. And we had originally started off using a Swagger and OpenAPI parser library, but we ended up giving up on it because it didn't scale very well, especially with that amount of files. And it would just sometimes hang, giving you no kind of insight into why without really diving into it. It actually originally appeared like it was a disk writing issue, which I was trying to debug for a while, only to realize that this parser was just breaking on us. And some specs are very weird, and the parser is too picky for it. So we may have like a mostly valid spec with a field that doesn't quite conform to the Swagger spec, but we still want to include, like that data might still be irrelevant, but we want to include the rest of it. So there are kind of limitations when using the Swagger library to parse that. that we weren't able to get past. So we just end up writing our own version of, it's basically just reading a bunch of dictionaries. And yeah, occasionally the parser would just die when reading a large bunch of files. So when we're generating our final output, this is just a screenshot of it running through, it would look something like this in our logs, where it would pass a bunch of them, exclude any blacklisted ones, and also exclude any invalid JSON. And on our data set of about 67,500 Swagger files, we ended up with an output.json file, collating all of those into about 2.8 gigabytes. This excludes a large chunk of the scrape data that we had, such as Google APIs, Azure, Swagger Pet Stores example, and Amazon, as these are all usually the same specs. And these are ready to be compiled with Kiterunner. And so Kite Builder, which is the tool that we use for passing all these specs, was able to, this is essentially how we'd use it, just do Kiterunner parse and pass in any of the parameters you want. It also adds a convenience tool for passing the CSV data we saw Shubs mentioned with the BigQuery. And so if you wanted to do that, you would just pass something like this with the CSV file in the format that it would come back from BigQuery. And it would save a bunch of JSON files into our scraping directory, which we could then use this parsing tool to go through and pass the whole scraping directory into an output or whatever you want to call your JSON file. So in here we call it kites.json.
So as Pat said, we took a whole bunch of these Swagger files, and we really wanted to formalize the spec into something that was usable to create web requests out of. So we took a bunch of JSONs and then rewrote our schema into Golang. And usually that's pretty good, except for the part where JSON's a very dynamic language, and it doesn't statically type very well. That and developers are very liberal with how they put things into JSON. So, for example, Swagger allows you to specify the content type that a request expects and will respond with. So, for example, however, here we have a developer that decided kindly to include the content type separately, completely ignoring the consumes endpoint that's provided for them. Here we have a developer that decided to be very explicit with how they wanted to do query parameters. Now, instead of specifying parameters inside the Swagger body, they decided to use their own custom format for the query parameters, resulting in something we can't really parse or use in any shape or form. In this case, we have a developer that probably forgot halfway what they were doing, and they kindly told us that there is a body to this request. They just don't tell us what this body contains. And I guess it's left as an exercise to the reader to figure out how to submit data to this request. Finally, we have a developer that thought they were trying to be very helpful. And here they specify the format as something returned by charts. That'd be great if they also included the charts endpoint in this API spec. Unfortunately, they didn't. And then we have what I think was my favorite from all of the data we analyzed. This developer wasn't quite sure how to format their data, so they left a placeholder. Thankfully for us, we know what that placeholder is. So just a few takeaways from learning to parse all of this into a strictly typed format. First of all, you can't really trust developers with anything because they're not going to do the right thing. The second thing is that statically typing JSON is incredibly difficult. And the way we got around that was using an intermediate data type for how we store our format, which effectively becomes the kite format that you will be using. So the second major challenge we had in engineering this tool was being able to handle wildcards. And if anybody's done some casual brute forcing before, the worst thing you can have is your output being flooded with a whole bunch of garbage requests. So as Mike previously explained, API brute forcing in this contextual aware environment is very fundamentally different from normal brute forcing. You often have directories and web servers that don't respond the same way anymore. Previously, they would 302 if a directory gave you the full path, but not the appending slash. Or you would have APIs that just straight up don't respond unless you supply the right endpoints or the right headers or even the right body type. And even more so, the current brute forcing landscape attempts to address wildcards and invalid results with using status codes. But in this landscape, you can't really trust status codes at all. You'll have web servers that give you 500 errors where it's a completely correct path, but you're just missing some header or some validation element. You have web servers that will 404 you, even though the most of your path is correct, but you've supplied the wrong user ID. So technically you're nearly there, but still it's a 404. And then, as we had before, you have web servers just straight up lie to you and just always return status 200, which is incredibly unhelpful. So the other case that you have to think of is that we now have applications that can virtually route multiple APIs together. Here we have an Nginx config that routes three different routes to three separate applications. And you have to keep in mind, this means that each application may potentially handle invalid input differently. So, for example, the admin application might 500 if you supply a wrong path, whereas the mail application might straight up 403 or 401 you for invalid permissions. And the way we solved this was not through machine learning, but through a whole bunch of heuristic analysis. And what do we mean by heuristic analysis? What we did was we decided to take a whole bunch of baselines. So in the examples before, we have admin and mail. For each of these directories, we would take a whole bunch of requests that would attempt to figure out what the expected response code, content length, how many words are coming back, how many lines are coming back, and use this to establish a heuristic for how the admin directory should respond. From this, we can then deduce anything that deviates from this baseline for the admin directory will then actually be considered probably an interesting result that isn't probably one of the default responses. Now, we've also implemented a whole bunch of other heuristics for cases we saw that you can't really detect through algorithms or like heuristics. And these were things like annoying cases where the AWS Elastic Load Balancer would always respond the same way if you supplied a certain header. So we have additional heuristics to help pick those things up. Now, obviously, all of the security experts that use tools want to be in control, and some of them really hate technology. So we let you turn these features off if you really don't like our algorithms. Now, we've also built this tool in mind with trying to handle the obvious edge cases where you're running this kind of content discovery brute forcing tool. We've all had cases where you're sending a lot of requests and the web server might be behind a certain big IP-based load balancer or like web application firewall. And then suddenly after sending 50-something requests in a second, all your requests start getting sinkholed, like they don't respond anymore. In these cases, we intelligently detect that a host has started abnormally responding the same way, and we quarantine that host to, one, save web requests, but also to make the user aware that this is probably a host that requires special care, either through different rate limits, different delays, or maybe a different IP address. Now, obviously, we've done a whole bunch of talk about how we can do these detections, but that doesn't really help us if the tool runs really, really slowly. I think over the past few years, as Mike has mentioned, we've gotten tools to be gradually faster and faster. And I think it's pretty easy at this point to write a tool in Go or Rust that will hit one host very, very quickly. But what we've done is we've figured out how to go quickly on lots and lots of hosts. Because at Asset Note, scanning one host really doesn't suit this really big attack surface. What we have here is across the same number of threads scaled on the same size box, scaled across multiple hosts. In this case, we're doing 5 concurrent hosts at a second. We're averaging 30,000 requests every second, compared to existing tooling, which will probably cap out around 5,000 or 6,000 requests on a single host. Admittedly, this is a bit of a contrived example. Realistically, no web server is going to respond at thousands of requests per second to your input. But in a more realistic workload, we're looking at around splitting, say, 1,000 threads across maybe 200 hosts, and we're averaging approximately 26,000 requests a second. Instead of having like one server being slammed, we prefer to distribute our load across multiple, and this way we increase our scanning throughput and give us a whole lot more results in a much shorter time period. So as part of trying to go really, really fast, we encountered a whole bunch of, I guess, challenges along the way. The first challenge we hit was, obviously, we started hitting connection limits on servers. When you try to open 100 TCP sockets, some servers just don't like that. So the way we resolved that was we decided to use long-lived connections, and we structured our concurrency method to strictly limit how many connections can be made to a server at any given time. Then after you get over that scaling problem, you realize that now I'm trying to open up requests to hundreds of hosts at once. And my laptop with its measly 512 file descriptors can't handle it. Unfortunately for us, there is no good solution for this aside from telling the user that they're doing something stupid and asking them to fix it themselves. Admittedly, the only way to stop this is to stop the user from shooting themselves in the first place. After that, you realize that now we can open lots of connections and we can send lots of requests. Where is all my time going? It's spent on context switching. Now, there's two aspects to this. One is internally, since we use a lot of Go routines, we spend a lot of time waiting on each other to give us information. So we structured our concurrency to minimize these waits entirely by batching up work and handling it with quite a unique parallelism method. The second part of this is that you start getting stuck on kernel context switches because now you're just waiting on syscalls for reads and writes from TCP sockets. Admittedly, there is no good solution to this at the moment. I'd love to implement the tool with an IO ring-based HTTP client, but it just doesn't exist yet. And then finally, we realized that once we've optimized out our connections, our context switching, we realized we're stuck on garbage collection. Since Go is a memory-managed language, this is quite unique to, writing tooling. And the way we solved that was simply to remove all the allocations we needed. And this means that while we're scanning, we will have minimal interruptions from the Golang garbage collector to try to fix up what we've made. So that being said, with the tool that we're releasing today, what will you get? You'll get some mad ASCII art from our very own James Hebden. Beyond that, we'll also provide conversion between standard word lists, JSON files, and our custom kite files. So this means you can interchange between these three formats if you want to use it with your own tooling, or you want to modify what the kite files look like. We've added built-in loading and caching of wordlist.assetNode.io word lists into the tool. So this means that where you're running the tool on a box where you, for example, don't have the word list yet, or you're trying to find a different content discovery type, but you don't necessarily have XML output, or you don't have ASPX word lists, you can automatically load the AssetNode word lists with the tool by itself. Just by specifying a parameter, we'll pull the word list down, cache it on disk, and in future scans, you can also use this at the same time. We also add a whole bunch of filtering and control options for your scanning. So you can add delays, you can skip our heuristic checks, you can filter on specific APIs that you want to scan, you can force specific methods if you know APIs do certain things, you can add your own headers, and you can sort of append as many word lists as you wish as you require. Another neat feature is we've found through our testing is some targets and some attack surfaces decide to use Okta or some other type of access gateway across their entire attack surface. Now, instead of showing you millions of redirects, you can opt to blacklist specific hosts where these requests will go to, and will simply save you the time and effort of filtering out that stuff. Finally, we also supply a way of reconstructing requests from the output. Now, what this means is that often with displaying the output, we can't be super verbose with what headers you have, what the body is, what specific things went into this request to cause an error. So we offer a way to replay a request and also proxy this request through your favorite internet proxy, like OWASP-ZAP. In addition to this, in addition to API scanning, we also provide good old vanilla API, normal brute forcing. So you can take it back to your dir search roots and even use the same dir search word lists because we have compatibility for those kind of things. So let's have a little chant towards the demo gods. I'm just kidding, we pre-recorded this. So here we have Kiterunner running across an attack surface that's a couple thousand hosts. We're running it with 200 max parallel hosts with 5 connections each. And what's happening here is that through every baseline directory that we're scanning, we perform a whole bunch of pre-flight requests, and then we start trying to figure out what requests are important and what's not. We're sending about 22,000 requests a second, which is going at a decent pace for what's effectively a medium instance on AWS. Now, you may be thinking, if we're sending so many requests, what's happening? There's our first one. And what we see here is we might not know why this request 500. So what you can do is you can take it to the replay, and then this will reconstruct the entire request, including headers, and show you why exactly this request resulted in a certain response. Let's go back and see what else came through. We can see that these specific API endpoints deviated from our baselines. And looking at this product endpoint, we can see that after we replay this request, this gives us a whole bunch of API information. So
now that Sean has built the tool, we've collected the data set. What's left is to apply the concepts and really prove to everyone that our ideologies and our theories on content discovery have value when it comes to security impact. So the first thing is, how do you find all the APIs worth brute forcing? Now there's this huge list of APIs I've included on this slide. And for each one of these APIs, we've created an API signature such that you can identify these APIs by the response on the index page or a 404 page. So you can find that in this repo, in this directory. And in the signatures, we've included a census link as well as the signature itself for what you should be looking for in order to identify these APIs. Typically, you want to be able to identify these APIs before you put them through something like Kiterunner. You don't want to just blindly use Kiterunner across every host, as the results may not be as amazing. So here's a meme, there's cannot get slash, which is the default response from Express when it can't find the route that you're trying to request. Now, I love that response because it tells me that it's an Express JavaScript Node.js server, which means that it's most likely running API endpoints, which means it's most likely a good candidate to put through something like Kiterunner. Here's some more examples. As I said earlier, here's Express. Express also has a header, X powered by Express. Golang looks like this, where it just says 404 page not found. Spring Framework has a white label error page, and Flask has this specific not found error page as well. So it's actually quite trivial to identify these API endpoints, and on an attack surface, you can use these sort of indicators to see whether or not you should be running them through Kiterunner with the context-aware brute forcing. So here's an example. A normal content discovery tool would have made a GET request to /download, and that would have been a 404 not found, like we see in this response here. Most content discovery tools would have probably stopped here unless the word list was super extensive and had everything necessary after the download path. But with Kiterunner, we can see that we get a 200 response when we provide an integer after the download field. Now, the great thing about Kiterunner is that it pre-fills all of the placeholders. So if the Swagger specification had a placeholder for an integer or a string or a UUID, we automatically fill that out and request that in the requests. So we can see it's a 200 here. What happens when we visit the 200? We see that it's actually trying to read from the local, it's reading a local file. So it's trying to read 175.064.999.pdf from one of these directories locally. We would have never really found this if it wasn't for the fact that we were requesting this specific path with the integer filled out. This is a really good example of why using something like Kiterunner is more effective than most content discovery tools out there today. Another example is where you hit /API/user, and that gives you a 404 not found, because that's all you had in your word list. You didn't have anything else beyond that. But you notice how on this path, you can't rely on the response to tell you whether or not there is a further directory down. You don't know that there's something after API user. There's no 301 or 302 response when hitting this path. But with Kiterunner, we're requesting fully formed paths. So we request API user me, as that's something that we found in our Swagger specifications. And then later, we were able to find that it's actually pulling users based off a hash. And then we were able to return data for a user by hitting that specific endpoint. So with Kiterunner, you've got that extra context, and you've got that extra ability to find endpoints like these. Another example is, this one's great, actually, because this really proves why Kiterunner is a tool to be using for content discovery, especially for APIs. This is an Express.js server, and you can see a GET request to /user create is giving you a 404. So all of the content discovery tools you use now, if you just use a huge word list and you just use the default configuration of GET requests, you would have missed that anything existed here. But with Kiterunner, we can see that a post request to /user create is a 500 internal server error. And that's really interesting, because if a GET is a 404 and a post is a 500, that kind of indicates that the endpoint actually does exist. And all other current tooling would have missed this endpoint. So we can replay this request by using Kiterunner's replay feature, and we can see that it actually responds with a JSON error. With some more analysis, we used param miner to guess the rest of the parameters, and we were able to register users using this endpoint. Another example is, /get/images is a 404 not found. /get/images/ is also a 404 not found. So traditional content discovery tools would miss that. You would not see a 200 response for any of these two paths. But with Kiterunner, what we found is anywhere in the path, if we had /images/something after that, so images and a suffix, we found that it led to a 301. So we investigated this a little further, and we went to that path, and it said info 53254 blah blah does not exist. So then we tried /etc password, and it actually just returned the contents of the etc password file. So here's another example of where having this context-aware brute forcing is really valuable, because it was expecting something after the image's path. And only because our context-aware brute forcing found that there was something after that leading to a 302 response, we're able to then investigate it and find the etc password file. So here are some links before we end off this presentation so that you guys can get the tools. The Kiterunner tool and the Kite Builder tool are available there. We've also written a blog post that goes into depth about all of the work we've done and some of these examples as well. The API signatures, as well as the 2 data sets that we're releasing today. So routes large is probably a little bit, will take a little bit longer to run, but it will have much more coverage. And routes small if you're just in a hurry trying to brute force quickly. The other thing that I want to quickly note is all of the data that we've collected in this process, we've also made it available as a regular word list that you can use with your favorite content discovery tool. There's nothing locking you into using Kiterunner. It's just a tool that I'm sure Sean would love, people would use because he spent the last 2 months on it. But for the most part, you can use any tool you want with the data set we've created. So Swagger wordlist.txt is something you can use with FFuff or whatever else you want to use. The other thing I want to just quickly mention is the effectiveness of Kiterunner across a large number of hosts. So something that you might struggle with as a pen tester or as someone who's testing web applications is you've got a large list of hosts that you want to do content discovery on. Most current content discovery tools are not so great at this. However, Kiterunner is actually probably very well suited to this, and you should really try it if you are doing something like that. So that's all. Thanks, guys.
Great job, guys. I've got a couple of questions on the slide. Have you run into many issues with IP blacklisting or fail to ban or other tools when scaling up your scanning? And has this blocked you from checking all scan options effectively?
So I guess I'll answer this in 2 parts. There's the first part where it's establishing our corpus of data, and the second part which is doing our research. With establishing the corpus of data, admittedly, I don't think we hit that many blacklists. Some of them people did complain, but in our first part, we only did 1 pass over the whole set, and using zgrab, it sort of gives you a bit of reliability with retries. So yes, we would have missed some things, but with the current corpus size, I think it's relatively comprehensive and sufficient to cover it. In terms of your content discovery and like running Kiterunner itself against bounty targets, we have had some hosts that just straight up blacklist you after a certain number of requests, like they're having capsula or a big IP in front of it. In most of those cases, we just hop onto a different EC2 instance and then resume. So hopefully that answers your question about blacklists.
Awesome. Actually, a few questions. You guys have done a good job. How have scalability considerations changed for 1,000 requests per second on one server versus 1 request per second on 1,000 servers?
I think that's a really good question. So currently our concurrency model spins up a supervisor thread for every host, and then that has its own pool of threads. And scaling out that many requests is actually more efficient with having a supervisor for every specific host, because that means now all these targets you're scanning out once can proceed in parallel. Whereas traditional content discovery tools, if you try to scale it out, might do all of it into the same pool, and one incredibly slow host would just block the rest. Our current concurrency model does try to handle your one host very slowly and then many hosts at that one time. That's also how a delay option works if you have a very sensitive set of hosts and you want 1 request per second per host.
Okay. How do you intend to keep the Swagger set up to date
So the data set, for the most part, should be pretty solid to use for a long period of time because we do cover a lot of different diverse data sources. However, we do plan to eventually scan more of the internet for more parts, like more ports that we wanted to scan. And additionally, we want to see if we can scrape more of Swagger Hub, because I mentioned that Swagger Hub has maybe 400,000 Swagger specifications. If we could get access to the full 400,000, that would be incredibly valuable for this security research. That's something that we're still in the process of trying to get access to.
Awesome. This is a simple question. Is the name a reference to Khaled Hosseini? If not, what's the story?
Yeah, so it's not a reference to Khaled Hosseini, but Kiterunner is actually a reference to this kite running festival that happens in my hometown in Gujarat, which is called Uttarayan, where you normally fly kites and you cut other people's kites down. So that's basically why it's named Kiterunner. And yeah, that's the origin story.
So just to add to that, Shubs came up with the name, obviously with his history. The names that Pat and Sean came up with were terrible. So if you buy us a drink later, we'll tell you what they are, but they weren't really good. So.
I'd love to say I'm laughing at that, but it's actually the next question. How to scale requests per second, assuming you're doing it over Australia's fastest Indian internet?
You don't. We ran all of our tests and requests from US East 1, so it goes faster there.
So, are you going to do an Axiom floor?
Yeah, I mean, it's something that you could probably use with Axiom pretty effectively, but I'm pretty sure Pyrock, the developer of Axiom, will beat us to it.
So was this using HTTP 2 or 3? If not, what sort of performance effects do you think you would have?
So we've considered using things like HTTP 2 and 3 for our clients. The main difficulty there is that the current Go libraries supporting them aren't very efficient when you scale it up. So currently it only supports HTTP 1. I think pipelining in HTTP 2 might make it substantially faster, but most of the bottlenecks occur on the server side since now you're sending API requests. This might also be doing API processing. So even if you can send 500 requests in a second, you're going to be waiting quite a while for the server to respond to those. So it's doable, but probably not advisable.
All right, we're almost there. There's just a couple more questions. Was the name Kiterunner inspired by Kiteworks?
No, but we've found a lot of vulnerabilities in Kiteworks in the past.
Maybe a talk for another time. Does Kiterunner self-advertise user agent other? Did you feel the need to do anything like any spoofing to prompt responses on an arms race with,
So generally a pro tip is that we just use the Chrome user agent. So by default, we just use the Chrome user agent. So, sorry, sysadmins.
An oldie but a goodie. If you're targeting just one web API, and it's generally a normally provisioned prod box, during your testing, how long has it taken to scan with the short and with the long list?
That's a good question. I mean, the answer depends on two things. One is the latency to that server, and two is how quickly that server can respond to things. My experience has been with the short word list, if you run it in the same region, for example, we guessed it's in US East, and we spin up an EC2 instance in US East, with relatively low latency, you're looking at maybe a minute or 2 minutes at tops, maybe in the realm of 30 seconds if it's a very fast server.
And this is the last question. Are you running on one host at a time? Have you considered multiple hosts with CNC or other orchestration?
That's an exercise left for the reader.
Otherwise, give a round of applause for these guys.